Hello, my name is Nick Durkee, and today I'm going to be talking about my project on material estimation using neural networks with long-wave infrared and hyperspectral data. In this project, I'm using hyperspectral data. Consider a normal color image where you have a red, a green, and a blue image. And together they combine to make a picture that you might take normally with your phone. Consider that each of these images is sampled at different wavelengths. You have red at 450 nanometers, green at 550 nanometers, and blue at 700 nanometers. Now, if you consider you have many different wavelengths in between these, and if you're able to sample them, you could obtain many more images. Now, this isn't necessarily useful to you or not, but it is still potentially useful information that you could use to determine what's in a scene. Now, this is useful because this contains a large amount of information. Consider that if you sample all of the different 200 different wavelengths between 8 and 13 micrometers, then you have hundreds of images sampling a wide range of the electromagnetic spectrum, and this all contains very useful information that you could look at a single pixel and determine what's in that pixel. This is compared to traditional imaging, where you'd have to look around a range of pixels in order to figure out what exactly is in your scene. In hyperspectral, you should label every single pixel. However, it's not quite so simple. Hyperspectral imagery has a lot of components that obscure what you might want to look at. And what we want to look at is the ground emissivity. This is an intrinsic property of the material that if we are able to recover this ground emissivity, we could look at it and say, okay, this is paint, this is metal, this is a chair, this is a car, this is a couch, this is a person. And you can tell all this only by looking at a single pixel, and you could label every single pixel within your scene as such. However, you have an atmospheric components and temperature components which obscure this in your recovered radiance. The atmospheric components are properties of the atmosphere and the temperature of the atmosphere and particulates within the atmosphere that add and block some of the radiance from reaching your camera. And the temperature is also just depending on how hot your material is, and affects how much radiance is put towards the camera. Now, if we're able to estimate these components, we're able to undo them and recover our material emissivity such that we can label the materials within our scene. So in this project, I wanted to develop my own neural network training program for my own learning process, and also to fill a gap that is lacking within MATLAB and Python. I wanted an algorithm within MATLAB that I was able to simply specify the sizes and number of hidden layers that I wanted, as well as input and output data. It would take that and automatically initialize and train a neural network such that I might do it in PyTorch. In PyTorch, you have to write a fair amount of code to get it running. In MATLAB, the shallow neural network programs don't have batch training or any sort of modern training algorithms that I might like to use. And with this, I was able to write code that is able to perform just as well as code I wrote in PyTorch, and it's also much faster due to the simpler nature of the code. Because it doesn't have to account for different types of neurons or convolutional neural networks or any sort of complex architectures, it's able to propagate much, much faster than a PyTorch network might be able to. Now, onto the data I'm using for this project. In this project, I'm using HITEST, the Hyperspectral Thermal Emission Spectrometer. It's a hyperspectral camera that's mounted on a plane, and it scans the ground in swaths, as you see in the figure at the bottom. And it scans 256 bands between 7 and 13 micrometers. And in this, we have radiance data and also estimated material emissivity data. And for the scenes we're using the scene near California, and we're really only using one of these swaths due to the large amount of data. In the future, we could also work with different projects with different data and try to generalize this network to account for any different scene across the US. as given different locations and days, we're going to have different atmospheric parameters, and we'd want to train a network that would be able to account for all of that. However, this adds a much higher level of complexity that's simply not suited for this project. And in this, I wanted to test a wide range of parameters for a neural network, comprising of different learning rates varying between 10 to the negative first and 10 to the negative fifth, and also different hidden sizes. I wanted to be able to find the optimal parameters. And what I found was that we're able to have our optimal performance with a moderate learning rate of 2 times 10 to the negative fourth. And we also found that increasing the size of the network didn't actually make the training process more difficult in general. As we got up to the higher hidden sizes, we noticed a drop off and even a decrease in performance at times, but in general, we're still able to obtain better performance. We noted that we obtained our best performance with a hidden size of 300, despite the fact that we only have 256 components on the input. However, this creates a very large neural network. We have an input of 256, and then we have 2 hidden layers of 300, which creates a number of weights numbering over 100,000. Now, we want to reduce the number of input wavelengths in order to reduce the size of the network and also improve the amount of robustness, as we have a lot of data that's simply not very useful for training. And the way I chose to do this is via backpropagation. The idea behind this is that if a feature is important, small changes in that feature will result in very large changes on the output. Now, if I'm able to take the derivative of the output with respect to the input via backpropagation, note that when we forward propagate, we obtain the derivatives of each of the activation functions with respect to that layer. We're able to obtain a derivative. Note that this is separate for every single pixel, and we also have a derivative for every single input and output. So if we have 256 input wavelengths, 202 output wavelengths, and 100,000 pixels, we obtain a derivative matrix of 256 by 202 by 100,000. Now, if we want to see which input wavelengths are important, we simply take the RMS of all of these derivatives over the output and all of the different pixels, such that we get a 1 by 256 vector, which we plot on the right. And if we look at this vector, we know that many of the wavelengths are much more important, particularly if we know around wavelength 35 and also around 230. So if we look at these and we say, these are the important wavelengths, these are the ones we want to keep. And from there, we can say we want to keep 30 wavelengths. So we keep the highest 30 on this chart and get rid of everything else in our input radiance data. So we'd end up with a 30 by 100,000 input data, and we're still training towards the same 202 by 100,000 emissivity data. And when we do this, we know that we actually get a slight improvement in performance. Before we got an optimum performance of 0.0049, and with this, we know that we get optimum performance of 0.0045. In addition, we note that we don't really need that many features. We're able to get a pretty good performance with just 75 features, which is nearly a third of what we started with. However, if we want to get the absolute best performance, we note that we still want to have about 128, or about half of the input features. So in conclusion, we're able to develop a neural network trainer in MATLAB, which is more user-friendly and works just as well as PyTorch, and also trains faster. And using this neural network training program, we're able to train a neural network that goes from input radiance data, is able to recover our material emissivity extremely quickly. And then from there, that material emissivity could be used to identify what materials are in our scene. And using this trained network, we're able to backpropagate through it in order to determine what wavelengths are actually important for estimating that material emissivity. And once we did that, we're able to obtain better performance at reduced cost. In the future, I'd like to work with methane and other gas data that's also in this data set. it's also in this data set. Originally, I was going to try and train radiance data towards the estimated methane gas data. However, due to problems in the data set, I wasn't able to find any correlation between the estimated methane gas data and the input radiance data. Even with at least squares estimation, I found zero correlation between the two. Thank you, and if you have any questions, I will be available in class.